we just establish the relation of this. That means the limit can be calculated by using an integration. Okay, the volume of the solid of revolution. Suppose the function fx, the gravity function of x is rotate about the x-axis and form solid revolution like this. Then how to find the volume? We use the exact same trick for finding area. That is, we divide the interval AB into, let's say, n parts by using a vertical line, cut it out, right? And every object being cut with the cross section, and the cross section, right? For example, this one, the cross section is a circle. In order to be easy to calculate, we consider equal width or uniform width. Say delta x, right? So how we cut? What is the shape for each object being cut out? It looks like a frustum, right? Right. You take out one piece of the object, it looks like a frustum, but actually this is not a frustum because the side is not a straight line here. It is a curve. Okay, but when the x is small, right? When x is small, we use another familiarized object to approximate the area of this something like frustum. This is a so-called disk. A disk actually is a cylinder, circular cylinder with a very small height. Okay, so we want to find the area of the disk. Okay, not area, the volume. So how? Okay, now the object is divided by many disk, small disks. So, for example, the first disk. Okay, so we look at the first disk. Okay, originally this is A, and then this is x1. So the width is delta x, what we set. So this height. How about the base area? The base area here. So we want to find the radius of the base. Or we know this circle, right? The base is a circle. Well, what is the radius? So the radius here. So that means the radius is, okay, I use another. The radius is here. So what is the length here? Okay, the length here is just putting x equal x1 to the function. So this is fx1. So this is here also fx1. So the volume of this small disk is pi r square. Now the r is f1, take the square, right? Because fx1 is the radius. And then multiply by the height. So we get the volume of cylinder, the small disk. And then the next disk, also you just think about the radius of the disk, the second disk so-called. So this fx2. So the radius is fx2. So in order to find the volume, you just multiply pi. So this is a base area of the second disk, and then multiply by the height is a volume. So we sum up all these volumes, of small disks. Okay, so we calculate something. What actually we are calculating? This is the approximate area of the whole of the original object, right? And then I use a summation sign to represent the idea about. That is, we sum up all the stuff like this. And the I is running from 1 to n. Imagine you make the height of the disk tends to 0. That is, you divide the interval with infinity many parts, right? Subintervals. So take out the limit when n tends to infinity. Then it tends to the limit, and that limit should be the volume of the object. Okay, so but how to calculate this limit? So we have the relation like this. We can calculate the limit by using integration. Now you see the limit form. This one is gx multiplied by delta x. Okay, so you see this one. Also, a function multiplied by delta x and summation and take the limit. So we can calculate this one by using integration. So this is integration from a to b, and the stuff is not gx but this time pi fx, and dx replaced by delta x replaced by dx. So we have the volume. To sum up, we can find the volume exactly equals to the limit of this stuff, and we can use integration to help us to finish the calculation. The volume. That's why.